Tonight, we're going to break your brain. Not with complicated equations or abstract theories, but with something far more unsettling. We're going to explore scale, the way distances and sizes change as you move from Earth to the stars, to the galaxies, to the edge of everything. And here's what's going to disturb you. Your intuition, that thing you rely on to navigate the world, is completely useless out there. The universe operates on scales so extreme that your mind physically cannot process them. The jumps aren't gradual, they're violent. Each step up the cosmic ladder multiplies distances by factors so large that the previous scale becomes essentially zero. By the end of this journey, you'll understand why the universe refuses to make sense, and why that might be the most important thing to know about it. Before we dive in, if you enjoy these kinds of deep explorations of space and reality, a quick like or subscribe would really help this channel grow. It's a small gesture, but it makes a huge difference for me. Now, let's begin. Let's start with a simple question. How big is big? It seems like an easy question, but it's actually one of the most difficult questions in all of science, because the answer depends entirely on what you're comparing. A house is big compared to an ant. A mountain is big compared to a house. The Earth is big compared to a mountain, and the universe is big compared to everything. But here's the problem. Your brain treats all of these comparisons the same way. You understand that each thing is bigger than the last, but you don't really feel the difference. And that's because human intuition was never designed to handle scale. Think about how humans evolved. For millions of years, our ancestors lived on the African savanna. They needed to judge distances to water sources, to prey animals, to predators. They needed to estimate how many members were in a rival tribe, how many days until the seasons changed, how far they could travel before nightfall. These are all numbers that fit comfortably within a certain range. Distances of a few feet to a few miles, quantities of a few individuals to a few hundred, time spans of hours to seasons. This is the range where human intuition works beautifully. You can picture 10 apples easily. You can imagine walking 5 miles. You can sense the difference between a minute and an hour. But go beyond this range, and something strange happens. Your intuition stops working. Not gradually, but suddenly. Like a switch being flipped. Try to imagine 1,000,000 apples. You can't do it. Not really. You might picture a large pile, but that pile looks pretty much the same whether it contains 1,000,000 apples or 10 million. Your brain simply does not have the hardware to distinguish between large quantities. This phenomenon has a name. Psychologists call it number numbness. It's the tendency for humans to treat all large numbers as essentially equivalent. 1,000,000 feels the same as 1,000,000,000. A billion feels the same as 1,000,000,000,000. They're all just big numbers, and big means the same as big. Here's an example that might help illustrate this. If you had 1,000,000 seconds starting right now, that would be about 11.5 days. Not that long. You could plan your week around it. 1,000,000 seconds from now, you might be on vacation or finishing a project at work. But if you had 1,000,000,000 seconds, that's about 31.5 years. 1,000,000,000 seconds ago, it was the early 1990s. The Soviet Union had just collapsed. The internet barely existed. Most people reading this weren't born yet. And 1,000,000,000,000 seconds? That's about 31,700 years. 1,000,000,000,000 seconds ago, humans were painting on cave walls during the last ice age. Civilization hadn't been invented. Writing was 26,000 years in the future. The ratio between 1,000,000 and 1,000,000,000 is the same as the ratio between 1,000,000,000 and 1,000,000,000,000. They're both factors of 1,000. But your brain doesn't register this. A million, a billion, a trillion, they all blur together into the category of really big number. This is number numbness in action, and it's going to cause us serious problems when we try to understand the universe. Let me demonstrate this another way. Consider the thickness of a sheet of paper, about 1/10 of a millimeter. Now imagine folding that paper in half. The thickness doubles to 2/10 of a millimeter. Fold it again, and it's 4/10 of a millimeter. Keep folding. After 10 folds, the paper is about 10 centimeters thick, roughly the height of a coffee mug. After the 20 folds, the paper is about 100 meters thick. That's taller than the Statue of Liberty. After 30 folds, the paper is about 100 kilometers thick. You've reached the edge of space. After 40 folds, the paper is about 100,000 kilometers thick. You've passed the moon, and after just 51 folds, the paper reaches the sun. 42 folds of a single sheet of paper, and you've traveled 93 million miles. Each fold only doubles the thickness, but that doubling quickly escapes any reasonable intuition. And here's what's terrifying. Cosmic scale works the same way. Each step up the cosmic ladder isn't an addition, it's a multiplication. And when you multiply repeatedly, you quickly reach numbers that make human experience irrelevant. The problem is that humans think linearly, but the universe operates exponentially. Linear thinking means adding. If I walk 1 mile, then another mile, then another, I've walked 3 miles. Simple, intuitive, but exponential growth means multiplying. If I double my distance, then double it again, then double it again, I haven't tripled my distance. I've multiplied it by 8. And if I keep doubling, the numbers explode beyond all recognition. This is why compound interest seems like magic. It's why populations can grow from thousands to billions in just a few generations. And it's why cosmic distances leave our intuition gasping for air. Consider the difference between walking speed and the speed of light. A human walks at about 5 kilometers per hour. The speed of light is about 1,080,000,000 kilometers per hour. That's a factor of about 216 million. Your brain registers that light is faster than walking, but it doesn't really grasp how much faster. If you could somehow walk to the moon, which is about 384,000 kilometers away, it would take you about 8 years of continuous walking without sleeping or eating. Light makes that same journey in about 1.3 seconds. By the time you blink, light has already arrived. But even light, the fastest thing in the universe, takes years to reach nearby stars, and billions of years to cross the observable universe. Even the universal speed limit is pathetically slow compared to cosmic distances. Here's another way to see the failure of intuition. Think about the number of grains of sand on a beach. This is often used as an example of an unimaginably large number. A typical beach might have something like 10 trillion grains of sand. That's 10 with 12 zeros. An enormous number. But now think about the number of stars in the observable universe. Current estimates put this at around 200 billion trillion. That's 2 with 23 zeros. The number of stars in the observable universe is roughly 20 billion times larger than the number of grains of sand on a beach. If you assigned 1 grain of sand to each star, you would need 20 billion beaches to represent all the stars. And yet, when I say there are lots of grains of sand and lots of stars, your brain treats these as roughly equivalent. They both fall into the category of too many to count. This is the fundamental problem we face when trying to understand cosmic scale. Our brains were not built for this. The ancient Greeks suspected this problem. Aristotle argued that infinity couldn't actually exist because it would lead to logical contradictions. But he also recognized that human minds struggle with large numbers even when they're finite. The Greeks developed geometry in part because it allowed them to think about relationships between quantities without having to comprehend the quantities themselves. You don't need to know how large a triangle is to prove that its angles sum to 180 degrees. This abstraction was a workaround for the limits of human intuition. Modern mathematicians have developed even more sophisticated tools. Scientific notation lets us write enormous numbers compactly. 10 to the 23rd power is easier to write than one with 23 zeros. Logarithmic scales compress enormous ranges into manageable charts. But these are just notational conveniences. They help us manipulate numbers without truly comprehending them. The numbers themselves remain beyond intuitive grasp. Let me give you a physical demonstration of number numbness. Imagine you're looking at two dots on a screen, one representing the size of an atom and one representing the size of the observable universe. If the atom dot were 1 pixel wide, how many pixels wide would the universe dot need to be to show the true ratio? The answer is about 10 to the 37th power pixels. If your computer screen is about 2000 pixels wide, you would need roughly 5 times 10 to the 33rd power screens placed side by side. That's more screens than there are atoms in your body. You cannot visualize this ratio. No diagram, no animation, no metaphor can actually show you the true difference in scale between an atom and the universe. The best we can do is approximate, and every approximation lies to your intuition. This failure of intuition has real consequences. It means that when scientists talk about cosmic distances, most people nod along without truly understanding. A light year sounds like a big distance, and it is, but how big? Most people couldn't tell you within several orders of magnitude. The Milky Way is 100,000 light years across. Is that big? Compared to what? The nearest large galaxy, Andromeda, is 2.5 million light years away. Is that much farther than the width of the Milky Way? Your intuition says yes, it's farther, but it doesn't grasp that it's 25 times farther. And the observable universe is 93 billion light years across. Is that much larger than the distance to Andromeda? Yes. It's about 37,000 times larger. But these multiplications mean nothing to your gut. They're just abstract facts without emotional weight. There's a famous thought experiment called the total perspective vortex, from the science fiction series The Hitchhiker's Guide to the Galaxy. In the story, it's a torture device that shows you exactly how insignificant you are compared to the infinite vastness of the universe. Most people who enter it go insane from the revelation. This is fiction, but it captures something true. Our minds protect us from the full reality of cosmic scale. If you truly, viscerally understood how small you are compared to the universe, it might be psychologically devastating. Number numbness isn't just a cognitive limitation. It might be a psychological defense mechanism. But we can push against these limits. We can use analogies and thought experiments to stretch our intuition, even if we can't fully overcome it. We can develop emotional responses to large numbers, even when our brains can't truly process them. And we can use mathematics as a prosthetic for intuition, trusting the equations even when our gut can't follow. Let's try an analogy that might help. Imagine the entire history of the universe, all 13.8 billion years, is compressed into a single calendar year. January 1st is the Big Bang. December 31st at midnight is right now. In this cosmic calendar, each month represents about 1 billion years. Each day is about 38 million years. Each second is about 438 years. The Milky Way forms sometime in early March. Our solar system forms in early September. The first simple life on Earth appears around September 20th. Fish first appear around December 19th. Dinosaurs show up on December 25th, Christmas Day, and they go extinct on December 30th. The entire history of human civilization, everything from the first cities to the internet, occurs in the last 14 seconds of December 31st. All of recorded history fits into a single blink at the end of the cosmic year. This compression helps make cosmic time feel more tangible. It shows that we are newcomers, that our entire existence is a blip. But even this analogy fails at smaller scales. What happened in the first millisecond of the cosmic year, the first 380,000 years of the actual universe? Your intuition can't zoom into a millisecond and see billions of years worth of physics unfolding. The cosmic calendar helps, but it has limits. The failure of human intuition is the starting point for understanding cosmic scale. Before we can appreciate the universe's true vastness, we have to accept that our natural mental equipment is inadequate. This isn't a failure of intelligence or education. Einstein struggled with the implications of his own theories. The greatest minds in history have found the universe's scale humbling. We are all operating at the edge of what human cognition can handle. Here's one more example that might crystallize this. Consider the age of the Earth, about 4.5 billion years. That's an enormous time span. Life has existed for most of it. Continents have drifted across the globe. Species have risen and fallen. It seems like a complete history. But the universe was already 9.3 billion years old when the Earth formed. The Earth's entire existence represents only the last third of cosmic history, and the universe has a long future ahead of it. Stars will keep forming for trillions of years. The last stars won't burn out for 100 trillion years. The age of the Earth, which encompasses all of evolution, all of geological history, all of planetary development, is a tiny fraction of the time the universe will exist. When you realize that the entire story of Earth, everything that has ever happened here, represents less than 1/10,000th of the universe's total lifespan, the numbers become absurd. They stop meaning anything to your intuition. You understand them intellectually, but you don't feel them. This is why scale matters. It's not just about knowing big numbers. It's about recognizing that the universe operates on a level that human minds were never designed to reach. The jumps from planets to stars to galaxies to cosmic structures aren't steps on a ladder. They're explosions of magnitude that leave human experience far behind. And accepting this, accepting that your intuition will fail, is the first step toward truly appreciating the cosmos. Let's also examine how different cultures have tried to cope with the incomprehensible. Ancient Hindu cosmology described time in enormous cycles, called kalpas, each lasting 4.3 billion years. This is remarkably close to modern estimates of Earth's age, though arrived at through very different methods. The ancient Hindu texts weren't doing science, but they were wrestling with the same problem we face today, trying to stretch human minds to accommodate timescales that dwarf individual experience. The ancient Chinese conceived of the universe as fundamentally boundless, refusing to put edges on space or time. Buddhist philosophy speaks of countless world systems, each containing its own mountains and oceans and living beings. These traditions didn't have modern telescopes, but they intuited that the universe might be vaster than any simple model could contain. Even in the Western tradition, which often focused on smaller, more anthropocentric models, there were voices arguing for immensity. Giordano Bruno, the 16th century philosopher, argued for an infinite universe containing countless worlds. He was burned at the stake, partly for this belief. The human resistance to cosmic scale isn't just cognitive, it's sometimes emotional and even political. Today, we have the tools to measure cosmic distances with precision, but precision doesn't bring comprehension. Knowing that Andromeda is 2.537 million light-years away, as opposed to 2.5 million, doesn't make the distance more intuitive. The extra significant figures are just noise to your intuition. This is the paradox of modern astronomy. We've never known more about the universe's size, and we've never been less able to viscerally grasp it. The failure of human intuition isn't a problem to be solved. It's a condition to be acknowledged. We will never naturally feel the true scale of the universe, but we can build conceptual scaffolding that helps us reason about it. We can train ourselves to notice when our intuition is lying to us, and we can learn to trust mathematics even when it leads to conclusions that feel impossible. Let me share another demonstration that reveals just how badly our minds fail at cosmic scale. Imagine you're asked to draw a line representing time. On the left end, mark the Big Bang, 13.8 billion years ago. On the right end, mark today. Now, somewhere on that line, mark when the dinosaurs went extinct, 66 million years ago. Most people, when they do this exercise, place the dinosaur extinction mark somewhere around the middle of the line, or perhaps a third of the way from the right end. But the correct position is so close to the right end that you couldn't see the gap with the naked eye. 66 million years is less than half of 1% of the universe's age. If the line were 1 meter long, the dinosaur extinction would be less than 5 millimeters from the right edge. Your intuition puts it in the wrong place because 66 million years sounds like a long time. And it is, by human standards. But by cosmic standards, it's nothing. This same distortion affects how we think about space. When people imagine the solar system, they typically picture the planets fairly close together, separated by modest gaps. This is how most diagrams show it, because if they showed the true distances to scale, the planets would be invisible specks separated by vast empty spaces. The distance from the Sun to Neptune is about 30 times the distance from the Sun to Earth. But that's still within our solar system. The nearest star is about 7,000 times farther than Neptune. Your mental model of the solar system, whatever it looks like in your head right now, is almost certainly wrong. It compresses the distances to fit into your visual imagination, making everything seem cozier and more navigable than it actually is. Here's a thought experiment that might help correct this. Imagine the Sun is a basketball about 24 centimeters in diameter. At this scale, Earth would be a small bead, about 2 millimeters across, located about 26 meters away from the basketball. That's about the length of a basketball court. Jupiter would be a marble about 2.5 centimeters across, located about 134 meters away. Neptune would be a small ball about 5 millimeters across, located about 780 meters away, nearly half a mile from the basketball. And where would the nearest star be at this scale? Proxima Centauri would be another basketball, located about 6,800 kilometers away. That's roughly the distance from New York to Berlin. You shrink the sun down to the size of a basketball, and the nearest star is still on another continent. This is the reality that our intuition refuses to accept. Space is empty. Staggeringly, overwhelmingly empty. The objects in it, planets, stars, galaxies, are tiny specks separated by gulfs of nothingness that dwarf them completely. When you see a picture of the solar system with the planets neatly arranged in a row, you're seeing a lie. A necessary lie, because the truth wouldn't fit on any page, but a lie nonetheless. The same distortion happens with time. When you think about your life, you probably have a reasonably accurate sense of how long different periods lasted. Your childhood might feel like a significant chunk. Your 20s might feel like they went by quickly. But when you think about historical time, the distortion kicks in. The Roman Empire feels ancient, separated from us by a vast gulf of time. And it is old by human standards. But the Roman Empire existed roughly 2,000 years ago. The dinosaurs went extinct 66 million years ago. The dinosaurs are 33,000 times more distant in time than the Romans. Does your intuition register that ratio? Probably not. Both the Romans and the dinosaurs feel like they belong to the category of a long time ago, even though one is incomparably more distant than the other. And here's where it gets really strange. The dinosaurs ruled the Earth for about 170 million years. That's over 2,500 times longer than humans have existed. If dinosaurs were still around today, they would look back at their first appearance the way we might look back at an event that happened 300,000 years ago, which is roughly when modern humans first appeared. To a dinosaur, the beginning of the dinosaur age would feel as distant as the emergence of Homo sapiens feels to us. And yet the dinosaurs went extinct only 66 million years ago, which is a blink of an eye compared to the 4.5 billion year history of Earth, which is itself only a third of the universe's age. These nested scales of time make human history seem almost imaginary. Everything we've ever done, every civilization, every war, every discovery, every work of art, all of it has occurred in a period so brief that it barely registers on cosmic timescales. If you wrote the history of the universe as a book with 1 page per million years, all of human history would fit in the last word of the last sentence of the last page. Actually, that's too generous. All of human history would fit in a single letter of that last word. The failure of intuition isn't just about numbers being big. It's about the relationship between numbers at different scales. 1 million is big. 1 billion is big. But 1 billion is 1,000 times bigger than 1 million. Your brain knows this fact, but it doesn't feel it. You can say the words 1 billion is 1,000 times bigger than 1 million without any sense of what that actually means. The relationship between the numbers is just as incomprehensible as the numbers themselves. This is why analogies help, even when they fail. When I say that if the age of the universe were a year, human civilization would be the last 14 seconds, you get a visceral sense of how brief we are. You know what 14 seconds feels like? You can hold your breath for 14 seconds. The analogy translates an incomprehensible ratio into something you can feel. But the analogy also fails because you can't actually compress 13.8 billion years into a year. The compression itself hides information. What happened in each of those cosmic seconds? Millions of years of events, evolution, extinction, continental drift, all compressed into a moment too brief to examine. The universe is not built to human specifications. It doesn't care whether we can comprehend it. It exists at scales that make human experience irrelevant, on timescales that make human history invisible, across distances that make human travel impossible. And yet, here we are, trying to understand it anyway. That's either magnificent or absurd, depending on your perspective. Maybe it's both. In the sections that follow, we're going to walk through the great jumps of cosmic scale, from planets to stars, from stars to galaxies, from galaxies to the cosmic web, and finally, to the observable universe and whatever might lie beyond. At each stage, we'll see the numbers multiply by factors so large that the previous scale becomes essentially zero. We'll watch our intuition fail again and again, and perhaps by cataloguing these failures, we can develop a kind of humility that passes for understanding. So let's begin the journey. Let's walk through the great jumps of cosmic scale and watch our intuition crumble at each one. Let's see how big the universe really is, and accept that we'll never truly grasp it. Now, let's take our first step into the cosmic abyss. We're going to start close to home, with distances you might think you understand, and then we're going to watch everything fall apart. This is the first great jump, the leap from planetary scales to stellar scales, and it's already enough to shatter any comfortable sense of the universe as a navigable place. Let's begin with the moon. The moon is the closest celestial body to Earth, and humans have actually been there. We've walked on its surface, collected rocks, driven around in little buggies. It feels accessible. The distance from Earth to the moon is about 384,000 kilometers. That's far by everyday standards. If you could drive a car to the moon at highway speeds, it would take about 5 months of continuous driving. But this distance is still within the realm of human comprehension. We can point to the moon in the sky. We can see it without a telescope. We've measured it, traveled to it, and returned. When the Apollo astronauts made that journey in 1969, they traveled at about 11 kilometers per second. At that speed, they crossed the gulf between Earth and Moon in roughly 3 days. The radio signals they sent back to mission control traveled at the speed of light, taking about 1.3 seconds to make the trip. You can hear that delay in the recordings of the moon landings. There's always a pause, this lag, because the radio signals carrying their voices traveled at the speed of light. And even light needs time to cross the distance between Earth and the moon. Now, let's move out to the sun. The sun is about 150 million kilometers from Earth. This is roughly 400 times farther than the moon. At highway speeds, it would take about 170 years to drive to the sun. This is starting to escape human experience. No one has ever traveled anywhere close to the sun. No human will likely reach it for centuries, if ever. But the sun still feels somehow graspable. We see it every day. Its light warms our skin. We know it's a star, but it's our star. Close, enough to dominate our sky. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. This means that when you look at the sun, you're seeing it as it was 8 minutes ago. If the sun suddenly vanished right now, we wouldn't know for over 8 minutes. We'd keep feeling its warmth, seeing its light, orbiting the point where it used to be, all while the sun no longer existed. The delay is built into the fabric of reality. Let's keep going. The outer planets are much farther still. Mars, at its closest approach, is about 55 million kilometers away. But at its farthest, when Earth and Mars are on opposite sides of the Sun, that distance stretches to over 400 million kilometers. Jupiter is about 628 million kilometers from the Sun on average. Saturn is about 1.4 billion kilometers out. Uranus is about 2.9 billion kilometers. And Neptune, the most distant major planet, orbits at about 4.5 billion kilometers from the Sun. The Voyager 1 spacecraft, launched in 1977, took 12 years to reach Neptune's orbit, and is still traveling outward. As of now, Voyager 1 is about 24 billion kilometers from Earth. That's the most distant human-made object in existence. It's been traveling for nearly 50 years, moving at about 17 kilometers per second, one of the fastest speeds any human artifact has ever achieved. And yet, after nearly 5 decades of constant travel through the vacuum of space with nothing to slow it down, Voyager still hasn't traveled one full light day from Earth. This is roughly the distance to the heliopause, the boundary where the Sun's influence ends and interstellar space begins. The true edge of the solar system, the Oort cloud, extends perhaps 2 light years from the Sun. Voyager 1 has covered less than 0.1% of that distance. At its current speed, it would take Voyager 1 about 70,000 years to reach the Oort cloud's outer boundary. 70,000 years ago, modern humans were just beginning to spread out of Africa. The entire history of human migration, the peopling of every continent, the rise and fall of every civilization would fit into the time it takes Voyager to crawl to the edge of our solar system. Let me put this another way. The solar system is not just the planets. The planets occupy a tiny inner zone, like a campfire in the middle of a vast dark plain. Beyond Neptune lies the Kuiper Belt, a ring of icy debris that includes Pluto and thousands of similar objects. The Kuiper Belt stretches out to about 50 times Earth's distance from the Sun. Beyond that is a vast empty gulf, and beyond that is the Oort cloud, a spherical shell of icy debris that marks the true boundary of the Sun's gravitational domain. This structure, the full solar system, has a diameter of perhaps 2 light years, light itself traveling at 300,000 kilometers per second, takes 2 years to cross from one side of the solar system to the other. Now here's where the first great jump begins. We've been talking about distances within our solar system, distances measured in billions of kilometers or fractions of light years. These are enormous by human standards. They dwarf anything in everyday experience, but they are absolutely nothing compared to the distances between stars. The nearest star to the Sun is Proxima Centauri, part of the Alpha Centauri system. It sits about 4.24 light years away. That's roughly 40 trillion kilometers. Let me try to make this concrete. If the Sun were the size of a basketball sitting in New York City, the nearest star would be another basketball-sized object in Los Angeles. Everything in between, thousands of miles of continent, would be empty space. That's how sparse the stellar neighborhood is. Here's another way to think about it. The distance from Earth to the Sun is 1 astronomical unit, or AU. The distance to Proxima Centauri is about 268,000 AU. The jump from planetary scales to stellar scales multiplies distances by a factor of hundreds of thousands. This isn't a step, it's a chasm. Consider what this means for space travel. The Voyager 1 spacecraft, traveling at about 61,000 kilometers per hour, would take roughly 73,000 years to reach Proxima Centauri if it were headed that direction, which it isn't. 73,000 years is longer than all of human civilization. Agriculture was invented about 10,000 years ago. Writing appeared about 5,000 years ago. The Great Pyramid of Giza was built about 4,500 years ago. If ancient humans had launched Voyager 1 toward Proxima Centauri during the Stone Age, it still wouldn't arrive for another 60,000 years. The spacecraft would outlast every empire, every religion, every language. It would still be traveling when whatever replaces humanity looks up at the stars and wonders if anyone else is out there. What if we could travel faster? The fastest spacecraft ever built relative to the Sun was the Parker Solar Probe, which reached speeds of about 692,000 kilometers per hour near its closest approach to the Sun. It achieves this by falling toward the Sun, converting gravitational potential energy into kinetic energy. At that speed, reaching Proxima Centauri would still take about 6,500 years. Faster, yes, but still incompatible with human timescales, with human civilization, with human patience. What about light itself? Light is the fastest thing in the universe. Nothing with mass can ever reach light speed, and even light takes over 4 years to cross the distance to Proxima Centauri. When you look at the Alpha Centauri system through a telescope, you're seeing light that left those stars more than 4 years ago. You're looking into the past, and if something happened there, an explosion, a change, a signal, you wouldn't know for over 4 years, because that's how long the information takes to arrive. This introduces a concept that's fundamental to understanding cosmic scale, the light year. A light year isn't a measure of time despite the name. It's a measure of distance. Specifically, it's the distance that light travels in 1 year. Since light travels at about 300,000 kilometers per second, and there are about 31.5 million seconds in a year, a light year works out to roughly 9.5 trillion kilometers. That's 9.5 trillion. A number so large that writing it out in full would take 17 digits. When astronomers say that Proxima Centauri is 4.24 light years away, they're saying it would take light itself, traveling at the maximum possible speed in the universe, over 4 years to make the journey. And light is fast, unimaginably fast, yet even light crawls when measured against the distances between stars. Let's zoom out a bit further. Proxima Centauri is the closest star, but most stars in our neighborhood are much farther. Sirius, the brightest star in our night sky, is about 8.6 light years away. That's twice as far as Proxima Centauri. Sirius is so bright, not because it's especially close, but because it's genuinely luminous, about 25 times more luminous than the Sun. If it were at the same distance as Proxima Centauri, it would be even more brilliant in our sky. Vega is about 25 light years away. Arcturus is about 37 light years away. Polaris, the North Star, is about 430 light years away. When you see Polaris tonight, you're seeing light that left during the Renaissance, before the telescope was invented, before Galileo turned his instrument toward Jupiter, before Newton formulated gravity, before the modern world existed. The stars in the night sky form an illusion of proximity. They look like they're all sprinkled at roughly the same distance, like lights on a dome. Ancient people believed exactly this. They thought the stars were fixed to a celestial sphere rotating around Earth. The Greeks called this sphere the firmament. It seemed obvious. The stars moved together across the sky, never changing their positions relative to each other. They must be attached to something, but in reality the stars span enormous ranges of distance. Some are nearby, cosmically speaking, others are thousands of light years away. The apparent dome of stars is a projection, a flattening of three-dimensional space onto your two-dimensional retina. The first great jump, teaches us that interstellar space is genuinely empty. Not just metaphorically empty, not just relatively empty, but staggeringly, overwhelmingly empty. The average density of matter in interstellar space is about 1 atom per cubic centimeter. Compare this to Earth's atmosphere at sea level, which has about 25 quintillion molecules per cubic centimeter. Space is about 25 quintillion times emptier than the air you're breathing right now. When spacecraft travel through interstellar space, they're essentially traveling through nothing. There's no wind, no resistance, no medium, just the occasional hydrogen atom drifting through the void. This emptiness has profound implications. It means that if you were somehow stranded in interstellar space, you would see almost nothing. No nearby stars, no planets, just distant points of light scattered across black infinity. The stars would look much as they do from Earth, perhaps a bit brighter without an atmosphere in the way, but still just points of light. You would have no sense of motion, no landmarks to pass, no way to judge distance or speed. You would float in a void so complete that your mind might struggle to process it. The first great jump also introduces a new way of thinking about the universe. Light, travel time. Within the solar system, light travel times are measured in minutes or hours. Light from the sun reaches Earth in about 8 minutes. Light from Jupiter takes between 35 and 52 minutes to reach us, depending on where Jupiter is in its orbit. Light from Neptune takes about 4 hours, but once you leave the solar system, light travel times stretch into years. 4 years to the nearest star, 8.6 years to Sirius, 25 years to Vega, 430 years to Polaris. This means that our view of the universe is always out of date. We never see the universe as it is. We see it as it was. Consider what this means. If Proxima Centauri exploded right now, we wouldn't know for 4 years. The light-carrying news of that explosion is still traveling toward us, crossing the vast gulf between our star and theirs. During those 4 years, we would continue looking at Proxima Centauri and seeing a normal, stable star. The explosion has already happened, but the information hasn't arrived. This is not just an observational limitation. It's a fundamental feature of the universe. Information, like everything else, cannot travel faster than light. Causation itself is limited by the speed of light. Events that are too far apart in space to communicate within a certain time period are said to be causally disconnected. They cannot influence each other not because of technological limits, but because of physics. This has implications for any dreams of interstellar communication or travel. If humans ever sent a message to a civilization around Proxima Centauri, the message would take over 4 years to arrive. Any reply would take another 4 years to return. A simple conversation would span nearly a decade. Ask a question, wait 8 years for an answer. Ask a follow-up question, wait another 8 years. This isn't a conversation, it's an exchange of time capsules. For stars farther away, the situation gets worse. A message to a civilization around Polaris, 430 light years away, would take 430 years to arrive and 430 years to return. The people who sent the message would be dead before the reply arrived. Their children would be dead. Their grandchildren would be dead. Their entire civilization might have transformed beyond recognition. Nations would rise and fall. Languages would evolve. Technologies would advance through revolutions we can't imagine. And the message would still be traveling, a whisper from a world that no longer exists, heading toward a destination that might not remember it was sent. Interstellar communication, even at the speed of light, is an exercise in cosmic patience. Interstellar travel is even more daunting. Even if we could build spacecraft that traveled at 10% of the speed of light, an engineering challenge of staggering proportions, it would still take 42 years to reach Proxima Centauri. A human who left Earth at age 20 would arrive at age 62. Their entire adult life would be spent in transit. They would leave behind everyone they knew, knowing they could never return in any meaningful way. And that's assuming everything worked perfectly. That the ship didn't malfunction. That the crew survived the psychological strain of decades in a metal container. That nothing went wrong in the void between stars. At 1% of light speed, a more realistic target for near-future technology, the journey would take 420 years. Multiple generations would live and die aboard the ship. The people who arrived would have no living memory of Earth. They would be the great-great-great-grandchildren of the original crew, raised entirely in the artificial environment of a spacecraft. Earth would be a legend to them, a story told by elders about a world none of them had ever seen. They would be born in transit, grow old in transit, and die in transit. Their entire existence defined by a journey that began centuries before they were born and would end centuries after they died. This is what the first great jump really means. It means that the stars, which look so close in the night sky, are actually separated by gulfs of such magnitude that human travel between them may never be practical. The distance to even the nearest star is so vast that it challenges every assumption we have about exploration, expansion, and the future of humanity. There have been proposals for faster spacecraft. The Breakthrough Starshot Initiative, announced in 2016, proposes using powerful ground-based lasers to accelerate tiny spacecraft, each weighing only a few grams, to about 20% of light speed. At that velocity, a probe could reach Proxima Centauri in about 20 years. Add another 4 years for signals to travel back to Earth at light speed, and you could potentially get data from Proxima Centauri in 24 years from launch. That's within a human lifetime, which is exciting. But the engineering challenges are enormous, perhaps insurmountable with current or near future technology. The lasers would need to deliver about 100 gigawatts of power, roughly the output of 100 nuclear power plants, all focused into a laser beam a few kilometers wide. The spacecraft would need to survive acceleration of thousands of g-forces. The sail would need to be almost perfectly reflective and incredibly thin, perhaps only a few atoms thick. And the spacecraft would need to function perfectly for 20 years in the harsh environment of interstellar space, without any possibility of repair. Even if Breakthrough Starshot succeeds, it would only send tiny probes, not humans, not colonies, just a few grams of sensors and cameras. The probes would fly past Proxima Centauri at 20% of light speed, taking pictures during a brief flyby that lasts only hours. They would have no way to slow down, no way to enter orbit, no way to linger. They would be there and gone, cosmic bullets passing through the night. And even this modest goal, a flyby by a gram-scale probe, lies decades in the future and requires technologies that don't yet exist. There are also rogue planets wandering through interstellar space. Worlds that have been ejected from their parent stars and now drift through the void unbound. Current estimates suggest there might be billions of such planets in our galaxy, wandering through the darkness without any star to warm them, These frozen worlds have no day or night, no seasons, no star to guide navigation. They are cosmic orphans, lost in the void. Some might retain internal heat from radioactive decay. Some might even have subsurface oceans, kept liquid by that internal warmth. But their surfaces would be frozen solid, colder than any naturally occurring place on Earth, adrift in the endless night between stars. And there are comets in the Oort cloud, icy remnants from the solar system's formation, that have been flung to enormous distances. Some of these comets have orbital periods measured in millions of years. They spend most of their existence in the outer darkness, far from any warmth, slowly drifting in elliptical orbits that eventually bring them back toward the inner solar system for a brief, spectacular appearance, before they retreat again into the night. These comets are messengers from the deep past, carrying material that hasn't been warmed since the solar system was young. The space between stars isn't just empty, it's a landscape of diffuse gas, wandering planets, and icy debris, all scattered so thinly that the word empty still basically applies. A spacecraft traveling through this region would encounter something only rarely, and that something would likely be a single atom or a grain of dust. The distances are so vast, and the matter so sparse that interstellar space might as well be nothing at all. This is the reality of the first great jump. Interstellar, distances are so vast that even our most ambitious proposals involve decades-long journeys for gram-scale probes. Human interstellar travel, if it ever happens, lies centuries or millennia in the future. The stars that seem to hang just above the horizon are actually separated from us by abysses that dwarf anything in human experience, and yet astronomers look at Proxima Centauri and call it nearby. In cosmic terms, the first great jump is just the beginning. Stars are separated by light years, but galaxies are separated by millions of light years. The scale multiplies again and again, each jump leaving the previous one insignificant. We've just taken the first step, the jump from planets to stars, and already any comfortable sense of the universe as navigable lies in ruins. The stars you see at night are just the beginning of the story. They're the closest trees in an enormous forest. And that forest is just one island in an ocean of forest that stretches beyond imagination. The universe has more jumps waiting, and each one will multiply the scale by factors that make everything we've discussed so far seem like nothing at all. We've crossed the first great jump, from planets to stars. We've seen how interstellar distances dwarf planetary distances by factors of hundreds of thousands. Now we're going to take the second great leap, from stellar scales to galactic scales. This is where the numbers become so large they stop functioning as numbers and become something closer to abstract symbols. Let's start with a basic fact. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. Think about that uncertainty for a moment. The difference between 100 billion and 400 billion is 300 billion stars. That uncertainty alone is larger than any number you've ever personally encountered. We can't count the stars precisely because many are dim, distant, or obscured by dust and gas. We're inside the galaxy, trying to count its contents, like a person standing in the middle of a dense forest, trying to count every tree. But the number is enormous. If you counted one star per second without stopping, without sleeping, without pausing for any reason, it would take you roughly 3,000 to 12,000 years to count all the stars in our galaxy. You could start counting when the Egyptian pyramids were being built and still not be finished today. These stars aren't uniformly distributed. The Milky Way is a spiral galaxy, shaped like a cosmic pinwheel with a central bulge and sweeping arms that extend outward. If you could somehow rise above the plane of the galaxy and look down, you'd see a majestic spiral pattern, with bright arms of young stars winding outward from a dense central core. The galaxy is roughly 100,000 light years across and about 1,000 light years thick in the disk. Though the central bulge is much thicker, perhaps 10,000 light years from top to bottom, our sun sits in one of the spiral arms called the Orion Arm or Orion Spur, about 26,000 light years from the galactic center. We're not at the center of anything special. We're in the suburbs, roughly halfway out from the core. Here's where the scale starts to become overwhelming. 100,000 light years is the diameter of the Milky Way. Remember that Proxima Centauri, the nearest star, is 4.24 light years away. The Milky Way is about 24,000 times wider than the distance to our nearest stellar neighbor. If the distance to Proxima Centauri were 1 inch, the Milky Way would be about 2,000 feet across, roughly the length of 7 football fields laid end to end. Light takes over 4 years to reach Proxima Centauri. Light takes 100,000 years to cross the Milky Way. If you send a signal from one edge of the galaxy to the other, it would arrive 100,000 years later. When that signal began its journey, modern humans were just emerging from Africa. The entire history of human migration, the peopling of every continent, the rise of agriculture, the invention of writing, the birth of every civilization, every empire, every religion, every scientific discovery, all of it would fit into the time that signal spent traveling. Civilizations could rise and fall many times over. Species could evolve and go extinct, and still the signal will be traveling, crossing the vast dark spaces between stars. The sun orbits the galactic center at a speed of about 230 kilometers per second. That sounds fast, and it is. At that speed, you could travel across the United States in about 3 minutes. You could circle Earth in just under 3 minutes. But even at this incredible speed, it takes the sun about 225 million to 250 million years to complete one orbit around the galaxy. The last time the sun was in its current position in the galaxy, dinosaurs were just beginning to evolve on Earth. The first dinosaurs appeared about 230 million years ago. Since then, the dinosaurs evolved, ruled Earth for over 160 million years, went extinct 66 million years ago, mammals took over, and humans eventually evolved. And the sun has only just now returned to approximately the same position in the galaxy where it was when dinosaurs first appeared. But the Milky Way is not alone. It has neighbors, lots of them. And this is where the second great jump truly begins. The nearest large galaxy to the Milky Way is Andromeda, also known as Messier 31. It sits about 2.5 million light years away. Remember, the Milky Way itself is 100,000 light years across. Andromeda is roughly 25 times farther away than our own galaxy is wide. If the Milky Way were a dinner plate sitting on a table, Andromeda would be another dinner plate about 6 feet away. The space between them would be essentially empty, containing only a few scattered dwarf galaxies and tenuous wisps of intergalactic gas. Consider what this means for any hope of intergalactic travel. Even traveling at the speed of light, which is impossible for anything with mass, it would take 2.5 million years to reach Andromeda. That's longer than humans have existed as a species. Homo sapiens appeared roughly 300,000 years ago. To reach Andromeda at light speed, we would need to travel for about 8 times longer than our entire species has existed. Every human who has ever lived, from the first modern humans in Africa to everyone alive today, fits into a span of time that's a small fraction of the journey to Andromeda. At more realistic speeds, intergalactic travel becomes incomprehensible. At 1% of light speed, a velocity we have no idea how to achieve but can at least imagine, Andromeda would take 250 million years to reach. That's longer than the entire age of the dinosaurs. The dinosaurs appeared about 230 million years ago, and went extinct 66 million years ago. Their entire reign, from the first small proto-dinosaurs to the asteroid impact that ended them, would fit comfortably within the journey time to Andromeda. The distances between galaxies are not just vast, they are, for all practical purposes, infinite. And Andromeda is our closest large neighbor. Most galaxies in the observable universe are billions of light years away. The light from distant galaxies has been traveling for billions of years to reach us. When we look at these galaxies through our most powerful telescopes, we're seeing them as they were billions of years ago, when the universe was younger and different. We're looking back in time, seeing galaxies as they existed before Earth formed, before our sun ignited, before the atoms that make up your body were assembled. The most distant galaxies we can observe are so far away that we're seeing them as they were just a few 100 million years after the Big Bang, when the universe was still in its infancy. Let's zoom out further and examine the structure that contains our galaxy. Galaxies aren't randomly scattered through space. They cluster together into groups and clusters, which themselves cluster into superclusters. It's hierarchy all the way up. Our Milky Way belongs to a collection called the Local Group, a modest gathering of about 50 galaxies bound together by gravity. The Milky Way and Andromeda are the two giants of the Local Group, each containing hundreds of billions of stars. The third largest member is the Triangulum Galaxy, with about 40 billion stars. The rest are dwarf galaxies, small collections of a few billion stars or less, satellites orbiting the larger members like moons around planets. The Local Group spans about 10 million light years, 10 times the distance to Andromeda. If you could somehow see the entire Local Group from outside, you'd see two large spirals, Milky Way and Andromeda, accompanied by one smaller spiral and dozens of fuzzy dwarf galaxies scattered around them. But even this is small. The Local Group is just one modest cluster in a much larger structure. The Local Group is part of something called the Virgo supercluster, which contains thousands of galaxies spread across about 110 million light years. The Virgo supercluster is named after the Virgo cluster, a dense concentration of galaxies about 54 million light years away that lies at the heart of the supercluster. The Virgo cluster alone contains over 1,000 galaxies, including giant elliptical galaxies that dwarf the Milky Way. These enormous galaxies sit at the center of the cluster, having grown fat by consuming smaller galaxies over billions of years. And even the Virgo supercluster is just a small part of something bigger. In 2014, astronomers made a remarkable discovery. Using careful measurements of galaxy velocities and distances, they mapped out the flow of matter in our region of the universe. What they found was that the Virgo supercluster is merely a lobe of an even larger structure called Laniakea. This supercluster of superclusters contains about 100,000 galaxies spread across 520 million light-years. The name Laniakea comes from Hawaiian and means immeasurable heaven. It's apt. Within Laniakea, galaxies are flowing toward a region called the Great Attractor, a massive concentration of matter that's pulling everything toward it. The Milky Way, along with everything else in Laniakea, is falling toward the Great Attractor at about 600 kilometers per second. That sounds fast by human standards, but at that speed, it would still take billions of years to reach the Great Attractor. The flows of matter in the universe happen on timescales that make human existence seem like a flash of lightning. But Laniakea isn't the largest structure. The universe contains countless superclusters, arranged into filaments and walls that surround enormous empty regions called voids. The cosmic web, as this structure is called, is the largest pattern in the universe. If you could somehow zoom out far enough to see the universe's large-scale structure, you see something that looks remarkably like a three-dimensional spiderweb, or perhaps like the neurons in a brain. Filaments of galaxies stretch across hundreds of millions of light-years, connecting dense clusters like threads, connecting knots. Voids, the empty spaces between filaments, can be hundreds of millions of light-years across, containing almost no galaxies at all. The Boötes void, discovered in 1981, is one of the largest known voids. It spans about 330 million light-years and contains almost nothing. If you were somehow located in the center of the Boötes void, you would see very few galaxies in any direction. The night sky would be darker and emptier than anything we experience on Earth. You would be surrounded by a bubble of nothing, an emptiness so complete that the nearest significant galaxies would be over 100 million light-years away. The largest known structures are truly staggering. The Hercules Corona Borealis Great Wall is a filament of galaxies stretching about 10 billion light-years across. That's about 70% of the diameter of the observable universe. If you could somehow travel along this structure at light speed, the journey would take 10 billion years, almost as long as the universe has existed. The Great Wall is so large that its existence actually poses problems for cosmology. Our models of how the universe evolved suggest that structures this large shouldn't have had time to form. The fact that they exist hints at processes we don't fully understand. Let me try a different kind of analogy to help convey the density of stars across these structures. Imagine that every star in the Milky Way were a grain of sand. How much sand would you have? A grain of sand is about 1 millimeter across, and a cubic meter contains about 1 billion grains of sand. 200 billion grains would fill roughly 200 cubic meters. That's the volume of a modest swimming pool. Every star in our galaxy, represented by a grain of sand, would fill a swimming pool. And our sun would be one of those grains, indistinguishable from all the others. You could reach into that pool, scoop up a handful of sand, and each grain would represent a star with potentially its own planets, its own history, its own possibilities, and you'd have no way of knowing which grain was our sun. But the Milky Way is not alone. It's one galaxy among roughly 2 trillion galaxies in the observable universe. Let that number sink in. 2 trillion galaxies. That's 2 followed by 12 zeros. If you filled a swimming pool with sand to represent the stars in the Milky Way, you would need 2 trillion swimming pools to represent all the stars in the observable universe. That's more than enough swimming pools to cover the entire surface of Earth multiple times over. Actually, If you covered the entire land surface of Earth with swimming pools, you'd have about 50 billion pools. You'd need to cover 40 Earths with pools to represent the stars in the observable universe. The second great jump also introduces a problem that the first jump only hinted at. Communication becomes essentially impossible across these distances. Within the solar system, communication delays are measured in minutes or hours. You can have a conversation with astronauts on Mars, though there's an awkward pause of several minutes between each exchange. Within the galaxy, delays are measured in years or centuries. A message to a star 100 light-years away would take 100 years to arrive. Between galaxies, they're measured in millions of years. A message to Andromeda would take 2.5 million years. Across the cosmic web, they're measured in billions of years. This means that different parts of the universe are effectively cut off from each other. A civilization in the Andromeda galaxy, even if it existed, could not communicate with us in any meaningful way. A message would take 2.5 million years to arrive. The reply would take another 2.5 million years. By the time the original sender received a response, 5 million years would have passed. Entire species could evolve and go extinct in that time. Civilizations could rise, flourish, and fall. Languages would change beyond recognition. The civilization that sent the original message might not even remember that it was sent. The cosmic web might be filled with intelligence. There might be billions of civilizations scattered across the universe, each one looking up at its own sky and wondering if anyone else is out there. But the distances ensure that this intelligence remains forever isolated. Each island of consciousness is separated from the others by gulfs of space and time that cannot be crossed. We could share a universe with trillions of other minds and never know it, never communicate with them, never even confirm their existence. And there's something else, something even more sobering. The universe is expanding. This isn't like galaxies moving through space away from each other. Space itself is stretching, carrying galaxies with it like dots on an inflating balloon. The farther away a galaxy is, the faster it's receding. Galaxies beyond a certain distance are receding faster than light, not because they're moving through space faster than light, which is impossible, but because the space between us and them is expanding faster than light can cross it. This means that most of the universe is already unreachable. Light from these distant galaxies can never reach us, no matter how long we wait. They are beyond our cosmic horizon, forever hidden from view. We can't see them, can't send signals to them, can't ever know what's happening there. They exist in the same universe as us, but we are permanently, fundamentally cut off from them. And this horizon is shrinking. The expansion of the universe is accelerating, driven by a mysterious force called dark energy. As the expansion accelerates, more and more galaxies are being carried beyond our cosmic horizon. Today, we can see light from galaxies billions of light years away. But those galaxies are receding from us, and eventually their light will be stretched into invisibility, redshifted beyond detection. One by one, the distant galaxies will disappear from our view. Given enough time, this process will erase most of the universe from our sky. The cosmic web that we can photograph today, the filaments and walls and voids stretching across billions of light years, will slowly disappear from view. Each distant galaxy will fade into invisibility, its light stretched beyond detection by the relentless expansion of space. The universe will appear to empty, not because the galaxies cease to exist, but because we can no longer see them. They will still be out there, spinning and evolving and perhaps harboring life. But they will be forever beyond our horizon, as inaccessible as if they existed in a different universe entirely. This is isolation on a scale that defies comprehension. Not just the isolation of one planet in the solar system, or one star in a galaxy, but the isolation of one pocket of gravitationally bound matter in an infinite expanding void. The second great jump reveals a universe of crushing isolation. Galaxies are islands separated by millions of light years. Galaxy clusters are archipelagos separated by tens of millions of light years. Superclusters are continents separated by hundreds of millions of light years. And all of these structures are embedded in a cosmic web that stretches across billions of light years, much of which is already beyond our reach and receding further with every passing moment. Let's pause and consider what the second great jump means for our understanding of humanity's place in the cosmos. We tend to think of Earth as our home and the solar system as our neighborhood. Perhaps, with enough time and technology, we might expand to other stars, becoming an interstellar species. This is the dream of science fiction, of Star Trek and Star Wars, and countless other visions of a galactic humanity. But the second great jump shows how modest even this dream is. Even if humanity spread to every star in the Milky Way, colonizing billions of planets across 100,000 light years, we would still occupy only one galaxy among 2 trillion. We would be confined to one small island in a cosmic ocean that spans billions of light years. The rest of the universe would remain forever beyond our reach, separated from us by distances that light itself needs billions of years to cross. Let me leave you with one more image before we move on. Imagine you're standing on a beach at night. The sand stretches to the horizon in every direction. Each grain of sand represents a star. The beach represents the Milky Way. Now, imagine that this beach is one of 2 trillion beaches scattered across an infinite ocean. Most of these beaches are so far away that you could never reach them, even if you traveled at the speed of light for the entire remaining lifetime of the universe. Some of them are so distant that you'll never even see them, their light forever unable to cross the expanding void between you and them. That's the second great jump. That's the scale of galaxies and beyond. The universe operates on scales that make human experience almost irrelevant. The distances are too large, the timescales are too long, the emptiness is too complete. Our spacecraft crawl across these gulfs at speeds that seem fast, but are actually pathetic compared to the distances involved. Our radio signals race outward at the speed of light, but even they need years to reach the nearest star, and millennia to reach stars we can see with the naked eye. We are isolated on our tiny world, surrounded by a cosmos so vast that crossing even the smallest gaps between stars would require technologies we haven't invented and patience we don't possess. And yet, this is just the beginning. We've made it to the scale of galaxies. Now, we have to understand what lies beyond. The second great jump took us from stellar scales to galactic scales. The final jump will take us to the observable universe itself and force us to ask what might lie beyond. We've made 2 great jumps, from planets to stars, from stars to galaxies. Now we're going to make the final jump, the leap to the largest scale we can measure, the observable universe itself. And then we're going to ask what might lie beyond. This is where scale becomes not just difficult to comprehend, but fundamentally alien to human thought. The observable universe is defined by a simple but profound limit. Light travels at a finite speed, about 300,000 kilometers per second. The universe is about 13.8 billion years old. Therefore, the farthest we can possibly see is the distance that light has traveled in 13.8 billion years. This creates a boundary, a cosmic horizon beyond which we cannot peer, no matter how powerful our telescopes become. It's not a physical wall. It's a limit imposed by the speed of light and the age of the universe itself. But there's a complication that makes this boundary stranger than it first appears. The universe has been expanding the whole time. Space itself has been stretching like the surface of an inflating balloon. So the light that has been traveling toward us for 13.8 billion years has been fighting against an expanding tide. The galaxies that emitted that light have been carried even farther away during the light's journey. It's as if you were swimming toward shore while the shore was receding faster than you could swim. The light eventually reaches us, but the source has moved much farther away in the meantime. The result is that the observable universe is about 93 billion light years in diameter. This number often confuses people, and rightly so. How can the universe be 93 billion light years across if it's only 13.8 billion years old? Shouldn't the maximum size be about 27.6 billion light years, twice the age in light years, one radius in each direction? The answer is expansion. The universe has been stretching the whole time, carrying distant galaxies farther away, even as their light travels toward us. The observable universe is larger than you'd expect because space itself has been growing throughout the entire history of the cosmos. 93 billion light years. Let's try to put that in perspective, knowing full well that we will fail. The Milky Way is 100,000 light years across. The observable universe is about 930,000 times wider than our galaxy. If the Milky Way were the size of a quarter, about 24 millimeters across, the observable universe would be a sphere about 22 kilometers across. That's about 14 miles in diameter. Our galaxy, which contains hundreds of billions of stars and spans 100,000 light years, would be a single coin in a sphere stretching from one side of a small city to the other. Let me try another comparison. The distance to Andromeda, our nearest large galactic neighbor, is 2.5 million light years. The diameter of the observable universe is about 37,000 times larger than that. The jump from intergalactic scales to cosmic scales multiplies distances by tens of thousands. Every jump we've made has multiplied the previous scale by enormous factors. From planets to stars, hundreds of thousands. From stars to galaxies, millions. From galaxies to the observable universe, tens of thousands again. The multiplications compound until the numbers become meaningless sequences of digits. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains anywhere from millions to trillions of stars. The total number of stars in the observable universe is estimated at around 200 billion trillion. That's a 2 followed by 23 zeros. Written out, it looks like this: 200,000 million, million. The number is so large that writing it doesn't help. Your brain sees it as just another big number, indistinguishable from a billion or a trillion. This is number numbness at its most extreme. If every star were a grain of sand, you would have enough sand to fill about 500 billion Olympic swimming pools. An Olympic swimming pool holds about 2.5 million liters. 500 billion pools would hold more than 1 quintillion liters of sand. The mass of sand required would exceed the mass of every beach on Earth by many orders of magnitude. You would need to cover the entire surface of the Earth, land and ocean alike, with sand several meters deep, to represent all the stars in the observable universe. Here's another way to think about it. One that's often quoted because it captures the scale so vividly. There are more stars in the observable universe than there are grains of sand on every beach on Earth. This comparison is roughly accurate. There are about 7.5 times 10 to the 18th grains of sand on Earth, counting every beach, every desert, every riverbed, every sandbox. And there are roughly 2 times 10 to the 23 stars in the observable universe. Stars outnumber sand grains by a factor of about 26,000. For every grain of sand on Earth, there are roughly 26,000 stars scattered across the observable universe. But the observable universe might not be the whole universe. In fact, it almost certainly isn't. The observable universe is just the part we can see, the region from which light has had time to reach us since the Big Bang. Beyond the observable universe, there is more universe. The question is, how much more? We don't know. Current cosmological models suggest that the universe is probably much larger than the observable portion. Some estimates, based on measurements of the universe's curvature, suggest the total universe is at least 250 times larger in diameter than the observable universe. If this is true, the observable universe is less than 1 trillionth of the total volume. Imagine a sphere 93 billion light years across, containing 2 trillion galaxies and 200 billion trillion stars. Now imagine that this sphere is less than 1 trillionth of the whole. The numbers become so extreme that they stop functioning as numbers. They're just symbols, placeholders for quantities that exceed any possible intuition. Other models suggest the universe might be infinite. In an infinite universe, there's no edge, no boundary, no limit. Space goes on forever in all directions, containing an infinite number of galaxies, an infinite number of stars, an infinite number of planets. Every possible arrangement of atoms would occur somewhere. In fact, every possible arrangement would occur infinitely many times. There would be infinite copies of you reading this exact script. Infinite variations where you stopped watching a minute ago. Infinite versions where you never started. The implications of infinity are so strange that physicists and philosophers have been arguing about them for centuries. We can't directly observe whether the universe is infinite. The cosmic horizon limits what we can see. No matter how long we wait, no matter how powerful our telescopes become, we can never see beyond the observable universe. The light from those regions hasn't had time to reach us, and due to the accelerating expansion, it never will. But we can look for indirect clues. If the universe had a certain kind of curvature, we might detect patterns in the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space. This radiation is the oldest light in the universe, released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. By studying tiny variations in this radiation, cosmologists can learn about the geometry of space itself. So far, measurements suggest the universe is flat or very nearly flat. Let me explain what this means. Space can be curved in different ways. It can be positively curved, like the surface of a sphere. On a spherical surface, parallel lines eventually converge. If you walk in a straight line on a sphere, you eventually return to your starting point. A positively curved universe would be finite but unbounded, wrapping around on itself like a higher dimensional sphere. Alternatively, space can be negatively curved like the surface of a saddle. On a saddle-shaped surface, parallel lines diverge. A negatively curved universe would be infinite, expanding forever in all directions. Or space can be flat, like an infinite plane. On a flat surface, parallel lines stay parallel forever. A flat universe would also be infinite, extending without limit in every direction. Current measurements of the cosmic microwave background, particularly from satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft, suggests the universe is flat to within a fraction of a percent. This implies that the universe is either infinite or so large that any curvature is undetectable. Either way, the observable universe is just a tiny patch in something vastly larger. If the universe is truly infinite, then the observable universe is nothing. Infinity minus 93 billion light years is still infinity. Our entire cosmic horizon, containing 2 trillion galaxies and 200 billion trillion stars, is a single point in an infinite expanse. The scales we've been discussing, the jumps from planets to stars to galaxies, become meaningless. Every finite scale is infinitely small compared to infinity. Our observable universe, which seems so impossibly vast, would be less than a speck, less than an atom, less than anything compared to the infinite whole. But even if the universe is finite, it's almost certainly far larger than what we can see. And what we can see is already incomprehensibly vast. The human mind evolved to navigate a world measured in meters and kilometers, timescales measured in days and years. We're trying to comprehend something measured in billions of light years and billions of years. Our cognitive architecture is simply not built for this task. We're using a calculator designed for household budgets to compute the economics of civilizations. The final jump also introduces another haunting concept: the cosmic event horizon. Because the universe is expanding, there's a limit to how far we can see. Light from beyond the cosmic horizon has not had time to reach us, but there's an even more unsettling boundary: the event horizon of the observable universe itself. Due to the accelerating expansion of space, galaxies beyond a certain distance are receding from us faster than light can travel through space. These galaxies are not just hidden from view temporarily, they are permanently unreachable. No signal we send will ever reach them. No spacecraft, no matter how fast, could ever travel to them. No information can cross the gap. They are beyond our universe in every meaningful sense. This isn't a violation of relativity. Nothing is moving through space faster than light. But space itself is expanding, and that expansion can carry objects apart faster than light. Imagine 2 ants on a rubber band that's being stretched. The ants might be crawling toward each other, but if the rubber band stretches fast enough, the distance between them grows despite their efforts. The ants aren't moving faster than their maximum crawling speed, but the expansion of the rubber band defeats them anyway. This is what's happening to distant galaxies. They're not flying away from us through space. Space is expanding between us and them, and that expansion is faster than light can compensate for. And here's the disturbing part. This horizon is shrinking. The expansion of the universe is accelerating, driven by dark energy, a mysterious force that pervades all of space. We don't know what dark energy is. We don't know why it exists. We only know that it's pushing the universe apart at an ever-increasing rate. As the expansion accelerates, more and more galaxies are being carried beyond our cosmic horizon. The observable universe is slowly emptying. Today, we can see light from galaxies billions of light years away, but those galaxies are receding from us. The light they emit today will never reach us because the expansion of space will outpace it. And the light we see from them now is ancient light, emitted billions of years ago. As time passes, that light will stretch into longer and longer wavelengths, redshifted by the expansion of space, until it fades into invisibility. One by one, the distant galaxies will wink out, not because they have ceased to exist, but because their light can no longer reach us. If you could watch the sky over trillions of years, using some impossible time-lapse camera, you would see distant galaxies slowly fade. Their light would stretch from visible wavelengths into infrared, then into microwaves, then into radio waves, growing fainter and redder until it disappeared entirely. One by one, the galaxies would vanish from view, carried beyond the horizon by the expansion of space. The universe would seem to empty, the sky growing darker and lonelier with each passing eon. Eventually, only the local group would remain visible. Our small cluster of galaxies, the Milky Way and Andromeda and a few dozen smaller companions, is held together by gravity. The gravitational attraction between these galaxies is strong enough to resist the expansion of space. While the rest of the universe flies apart, the local group will remain bound, slowly collapsing together over billions of years. In about 4.5 billion years, the Milky Way and Andromeda will collide and merge. But even this merger, the largest gravitational event our galaxy will ever experience, is tiny on cosmic scales. Two galaxies becoming one still leaves us as one galaxy among 2 trillion. The merger will reshape our night sky beyond recognition, but it won't change our fundamental isolation. We'll still be one island in a cosmic ocean that spans billions of light years. In the very far future, perhaps 100 billion years from now, any beings looking up at the sky from a planet in the merged galaxy would see only their own galaxy. Everything else would be gone, carried beyond the cosmic horizon by the expansion of space. They would have no way of knowing that the universe once contained 2 trillion galaxies. The cosmic microwave background, that faint echo of the Big Bang, would have stretched into wavelengths too long to detect. The evidence for the Big Bang itself would have faded into invisibility. Future astronomers, if any exist, might conclude that their galaxy was the entire universe, an island of matter in an infinite void, with no way to know that anything else had ever existed. This is perhaps the most profound implication of the final jump. The universe is not only incomprehensibly vast, it's also impermanent. The view we have today of billions of galaxies stretching across billions of light years is temporary. We happen to exist at a moment in cosmic history when the universe's structure is still visible. Future generations, separated from us by hundreds of billions of years, will inherit a cosmos that appears empty. The cosmic horizon is closing in. The observable universe is slowly emptying, and there's nothing we can do to stop it. Some cosmologists have called this the cosmic dark ages, a time in the far future when the universe will contain only isolated islands of matter, each one alone in an infinite void, unable to see or communicate with any other. The expansion of space will have erased all evidence of the cosmic web, leaving each galaxy cluster to face eternity alone. Let me return to the question of scale and what it means for human significance. We started this journey by noting that human intuition fails at cosmic scales. By the time we reach the observable universe, we're dealing with numbers so large they have no intuitive meaning. And beyond the observable universe, there might be infinity itself. What does this mean for us? Are we insignificant? Are our lives meaningless given the scale of the cosmos? I think the answer is more complicated than it first appears. Yes, in terms of physical scale, we are unimaginably small. The Earth is a speck orbiting a typical star in a typical galaxy in a typical corner of the observable universe, which itself might be a tiny bubble in an infinite or nearly infinite cosmos. By any geometric measure, we are essentially nothing. If you wrote the address of Earth in the universe, it would be something like Earth, Solar System, Orion Arm, Milky Way Galaxy, Local Group, Virgo Supercluster, Laniakea, Observable Universe, possibly surrounded by infinite more universe. At each level, we're one among billions or trillions, but scale isn't everything. The universe is mostly empty space and simple matter. Hydrogen atoms drift through the void. Stars burn through nuclear fusion, converting hydrogen to helium to heavier elements, but they're not thinking about it. Galaxies spin in silence, held together by gravity, but they're not aware of their own existence. Very little of the universe is complex. Very little contains information in any meaningful sense. And as far as we know, almost none of it is conscious. Consciousness, the ability to experience and reflect and wonder, might be incredibly rare. It might be the rarest thing in the universe. Earth might be the only place in the observable universe where atoms have arranged themselves into beings that can contemplate the cosmos. Or there might be others, scattered across billions of light years, each an island of awareness in an ocean of silence. We don't know. But either way, consciousness is precious. Not because the universe values it, but because it's genuinely unusual in a cosmos dominated by empty space and mindless matter. The universe spent 13.8 billion years arranging matter into stars and galaxies and planets. It took another 4.5 billion years on Earth for life to evolve from simple chemistry to complex organisms. And then, in just the last few 100,000 years, humans appeared. We developed language, which allowed us to share ideas across generations. We built civilizations, which allowed us to accumulate knowledge. We invented mathematics, which gave us a language for describing things we couldn't see or touch. And finally, we turned our attention to the stars, building telescopes that could see billions of light years, and developing theories that could explain the origin and fate of the cosmos. You are made of atoms that were forged in the cores of dying stars billions of years ago. Those atoms were scattered across space by supernova explosions, drifting through interstellar clouds for millions of years. Eventually, they were gathered into a new solar system by gravity, incorporated into a planet, and arranged by evolution into a living being. And now, in this moment, those atoms are aware of their own existence. They're contemplating the cosmos that created them. You are the universe looking back at itself, asking how big it is. That's not nothing. That's extraordinary. The final jump takes us to the edge of what can be known. Beyond the observable universe, there might be infinite space containing infinite galaxies and infinite possibilities, or there might be boundaries we can't imagine, laws of physics we don't understand, structures we can't perceive. There might be other universes entirely, separated from ours by dimensions we can't access. Some theories in physics suggest that our universe is one bubble in an infinite foam of universes, each with different physical laws, most of them sterile and lifeless, a few capable of supporting complexity and awareness. We don't know if these theories are true. We might never know, but we know this much. We are here on a small planet, orbiting an ordinary star, in a galaxy of hundreds of billions of stars, in a universe of trillions of galaxies, asking how big it all is. And the answer so far is that it's bigger than we can understand, bigger than our brains can process, bigger than any metaphor can capture. We've traveled from the comfortable distances of everyday life to the crushing vastness of the observable universe. We've watched our intuition fail at every step. We've seen the jumps from planets to stars to galaxies, each one multiplying distances by factors that obliterate the previous scale. We've peered beyond the cosmic horizon and wondered what might lie there. And through it all, we've learned that scale is not just a property of the universe. It's a fundamental challenge to human cognition. We are creatures of limited experience trying to comprehend something unlimited. We are finite minds grappling with the possibly infinite. Human intuition is a survival mechanism adapted to life on the African savanna. It was never meant to handle light years and billions of galaxies. When we try to apply it to cosmic scales, it simply breaks. But we can build new tools to extend our reach. Mathematics gives us a language for describing what we cannot picture. Telescopes give us eyes that see beyond human limits. Spacecraft give us reach beyond human grasp. And science gives us a method for testing our ideas against reality, even when reality exceeds our imagination. The universe is vast beyond comprehension. But we comprehend that it's vast. We know the numbers even if we can't feel them. We understand the structure even if we can't visualize it. And that's something. That's the beginning of wisdom. We've mapped the cosmic web. We've measured the expansion of space. We've detected the echo of the Big Bang itself. We've done all of this from a tiny planet orbiting an ordinary star, using brains that evolved to track prey and avoid predators. That's remarkable. That's worth celebrating. So the next time you look up at the night sky and see those points of light scattered across the darkness, remember what they represent. Each one is a sun like ours, separated from us by light years of empty space. Beyond those visible stars lie billions more in our galaxy. Beyond our galaxy lie trillions of others. Beyond them all, perhaps, lies infinity itself. And you are here. A pattern of atoms that has become aware of all this, looking up and wondering. The universe refuses to make sense on human terms. And that refusal, that challenge to our intuition, that confrontation with scales beyond imagining, might be the most important thing the cosmos has to teach us. We are small. We are brief. We are lost in a vastness that dwarfs all our achievements and all our dreams. And yet we are here, wondering about it all, trying to understand our place in something that exceeds all understanding. Thank you for taking this journey with me. If you found it valuable, a like or subscribe would mean a lot. The universe is vast, but you watch this exploration to the end, and maybe, just maybe, your intuition has stretched a little. The numbers still don't make sense. They never will. But perhaps you've made peace with that. Perhaps you've accepted that the cosmos doesn't cooperate with human comprehension and decided to wonder about it anyway. Sleep well tonight under those distant stars. Each one is a sun. Each one might have planets. And out there, across billions of light years, there might be other beings looking back, wondering about us, trying to make sense of a universe that refuses to be understood. We'll never meet them. We'll never communicate with them. The distances are too vast, the expansion too relentless. But knowing they might exist, knowing that consciousness might be scattered across the cosmos in islands of awareness separated by oceans of emptiness, that's something. That's a kind of cosmic companionship, even if we'll never shake hands. The scale is impossible. The distances are absurd. The numbers are meaningless. And yet, here we are, aware, wondering, alive, made of star stuff, contemplating the stars that made us. Good night, and may you never look at the universe the same way again.